Hi, my name is Jason Fournier, and this presentation is on the reliability and fault resilience optimizations for network on-chip architectures. The outline of this presentation will be as follows. First, we'll start with history, then we'll go into the introduction, background, current optimizations, ongoing research, conclusion, and finally, resources. So here's a timeline of on-chip communication architectures. In the early 90s, custom communication was well defined, yet a non flexible implementation. By the mid 90s, the shared bus method utilized a common backplane connection to define a standard interface. This was then followed by the use of a hierarchical bus, which used multiple shared bus interfaces when a single shared bus did not provide adequate connectivity. It could only support limited bandwidths and was not scalable for very high performance designs. In the mid 2000s, the bus matrix, which was comprised of several parallel buses, was being used to support high bandwidth systems but suffered from high cost overhead due to extensive bus wiring inside of the matrix. So, as electronic systems continued to become more and more complex, the need for a scalable communication protocol that could handle the bandwidth needs and provide reduced signal overhead to meet the demands of the gigahertz frequency realm was needed. So, what is a network on chip? Network on chips are an attempt to scale down the concepts of large scale networks. It is a packet switched on chip communication network designed using a layered methodology. Network on chips use packets to route data from the source to the destination processing element via a network fabric that consists of switches and interconnection links. So, why use an on chip network instead of global wiring? First off, electronic systems are becoming increasingly complex. Current multiprocessor designs have hundreds of components. Future complex systems are expected to operate in the gigahertz realm. So, a scalable communication fabric is needed to meet performance demands. It must meet quality of service and real time response requirement needs for heterogeneous systems. Secondly, integrated circuit technology has been rapidly advancing. Process technology is now in the deep submicron domain. At this scale, undesirable effects are more prevalent, such as inductive and capacitive coupling delays from long wire interconnects, increased transmission errors due to crosstalk, EMI, and synchronization failures, and decreased determinism due to manufacturing variations. Next, it uses a fully optimized structure. On-chip network structures link so that their electrical properties are optimized and well controlled, such as low and predictable crosstalk. Also, there is increased performance. Aggressive signaling circuits can reduce power dissipation by a factor of 10 and increase propagation velocity by 3 times. Sharing wiring resources maximizes efficiency and minimizes peak load idling. Higher bandwidths and multiple concurrent communication support. Finally, added modularity. On-chip networks define a standard interface, provides reusability and interchangeability of modules. Multiprocessor interconnection networks. There are two main types. First, there's the point-to-point interconnection, which processing elements are directly connected, either by direct or path communications. And switch-based interconnection networks, where the processing elements are connected via switch and the topology organizes the communication. Now we'll talk about the causes of faults. First off is the decreasing fabrication sizes, which leaves them susceptible to cosmic radiation, electrical interference from harsh industrial environments, and finally smaller threshold voltages that can lead to bit flips or crosstalk. Next is the decreasing transistor sizes, which reduces real-time predictability and fault reliability, and leads to non-uniform memory latencies from bus contention and increased mesh interconnects. And finally, increasing power densities, such as thermal spikes and gradients, which can cause hotspots and catastrophic failures. But now there are fault recovery methods that we're going to discuss, which include hardware redundancy, time redundancy, and information redundancy. For hardware redundancy, requires several copies of protected hardware. And there are two categories of hardware redundancy. First off, being passive redundancy, which bases its results provided by all hardware copies. One example would be triple module redundancy that utilizes three hardware copies and accepts matching results from two of three copies as the correct result. And secondly, the active hardware redundancy, which switches to correct redundancy component when faults are detected. It uses a reconfigurable router architecture and spare wire for the data layer link, and a fault-tolerant routing algorithm for the network layer. In time redundancy, it masks the impact of faults by repeating the same process several times. This introduces extra delay and can cause performance loss, as it may not be reprocessing the same data. The split link abandons faulty wires and continues transmission with the remaining structure. This reduces network performance and increases circuit complexity. There is also the partially faulty link recovery mechanism, which after identifying a fault, the transmitter resends the data until every wire receives the same data at least once. Then the receiver rebuilds the data by bit shifting. There is also the repeating operations redundancy method, where transient faults can be masked by repeating same processing several times. One example is the twice routing calculation scheme. So if the repeated results after second routing are the same, then they are correct. If not, a third calculation is performed and the correct result is arbitrated. In this scenario, there's no obvious delays for networks using long packets, but for networks using short packets, there will be obvious delays. There is also a soft error-tolerant network-on-chip router pipeline architecture. It requires two routing calculations, virtual channel arbitration, and switch arbitration to detect faults. If faults are detected, the extra two pipelining stages are necessary to roll back and repeat the routing calculation. And here is a diagram of a pipeline stage for repeating operations without faults and with faulty routing calculations. And in the retransmission time redundancy method, when packets exceed the fault recovery ability of routers and network interfaces, they are abandoned and retransmitted. Retransmission is a common fault recovery method for data recreation. With information redundancy, it copies the information directly or via a specified algorithm. The most common methods are either the flooding, routing for the network layer, or error correcting code for the data link and transport layers. With flooding routing, it directly transfers several packet copies over the network. A packet is accepted correctly when one copy packet is accepted correctly. This method achieves excellent reliability, but redundant packets increase network traffic and reduce network performance. So, error correcting code, the most common fault recovery method for the data path. It's used for detecting and correcting transient faults and network on chips caused by unreliable or noisy communications. There's an increased reliability by information redundancy. Encoders add redundancy bits to the original information. Decoders compare the original and redundant data and correct the error bits if necessary. Code types are selected based on reliability and overhead trade-offs. Example code types include Hamming code, Hasio code, and cyclic redundancy check code. So the most commonly used type of error correcting code is the Hamming code, which was created by Richard Hamming of Bell Labs in 1950 to correct errors in punch card readers. It detects two faults and can correct a single fault during data transmission. This is a popular technique for handling soft faults without degrading performance. It adds 3 parity bits to 4 bits of data, which is also referred to as the conventional Hamming code, but also exists a modified Hamming code as well as an extended Hamming code. So there's been a lot of ongoing research covering the topics that we've presented so far in this presentation. One of which being the fault observant and correcting real-time embedded design, which the authors of that article refer to as Forte, which utilizes a massive multi-core network on chip design to reduce overhead and jitter. It relies on message passing instead of shared memory for intra-processor communication, which can reduce overhead by an order of magnitude. It's shown to improve overall system scalability. It improves fault resilience by orders of magnitude by utilizing replication and task rejuvenation. So it increases performance by eliminating the use of shared memory, increases the overall predictability, and reduces controller memory contention. The last research paper we'll talk about is the optimized fault-tolerant buffer design for network-on-chip architectures. It relies on error correction code to protect against data errors by using an extended Hamming code to protect stored buffer data. It uses single error correction double error detection for 16-bit data with 6-bit redundancy. So in conclusion, as technology continues to decrease in size yet increase in complexity, the need for reliability and fault resilience optimizations will continue to grow. There are many current solutions for today's network-on-chip designs, but research needs to continue pushing forward to solve tomorrow's size, reliability, and power constraints in the sub-nano chip and terahertz processor realms. And new and clever hardware and software hybrid optimization designs could provide the necessary footing to increase the number of transistors fabs can reliably fit onto a network on chip. Thank you very much for listening.